There's a place in the universe so cold it defies imagination, where the very fabric of reality seems to slow to a whisper. Picture temperatures just a hair above absolute zero, the coldest possible state where atoms almost stop moving entirely. These frozen frontiers, like the hauntingly beautiful Boomerang Nebula or the vast, empty gaps between stars, aren't just cosmic curiosities. They might be the silent architects of life itself. What if the key to understanding our existence, and even the potential for life beyond Earth, lies hidden in these unimaginably cold depths? It sounds like science fiction, but the science behind it is very real, and it's rewriting what we thought we knew about the building blocks of life. Think about the coldest place you've ever experienced, maybe a winter night so bitter your breath froze in the air. Now multiply that cold by 1,000,000, and you're still not even close to the chill of these cosmic iceboxes. Yet, paradoxically, these extreme environments could be preserving the very ingredients that make life possible. In the freezing void, complex molecules survive for eons, shielded from the destructive heat and radiation that dominate warmer regions of space. It's like nature's own deep freezer, safeguarding delicate organic compounds until the perfect conditions arise for them to awaken. Scientists are now uncovering clues that these frigid zones might be where life's blueprint was first drafted, and where we could find evidence of alien biochemistry unlike anything on Earth. This isn't just about distant nebulae or abstract theories. It's a story that connects all of us. The same icy processes that might have seeded life elsewhere in the cosmos could be mirrored in the frozen cracks of moons like Europa or Enceladus, right here in our own solar system. What if the universe's coldest corners aren't barren wastelands, but cosmic cradles? By peering into these frozen realms, we're not just exploring space, we're unraveling the mystery of our own origins. So let's journey together into the cold, where the secrets of life may be waiting, preserved in ice and silence, ready to reveal their astonishing truths. Absolute zero isn't just an abstract number, it's the edge of what's physically possible. At -273.15 degrees Celsius, atoms lose nearly all their energy, freezing in place like dancers mid-step. But here's the twist: space doesn't quite reach this extreme. Instead, regions like the Boomerang Nebula flirt with temperatures just 1 degree warmer, creating pockets where time itself seems to slow. In these frigid depths, chemical reactions that would blaze in seconds on Earth stretch across millennia. This sluggish pace isn't a flaw, it's a feature. Complex organic molecules, the kind that could form life's foundation, survive here unharmed, shielded from the violent collisions that tear them apart in warmer environments. Consider how warmth speeds things up. A sugar cube dissolves in hot tea almost instantly. Now reverse that. In the cosmic cold, delicate structures like formaldehyde or hydrogen cyanide, fragile as spun glass, endure for ages. These molecules aren't just surviving, they're accumulating, drifting together like puzzle pieces in slow motion. Some researchers suggest this could mirror Earth's early conditions, where simple compounds stewed in icy comets or frosty asteroid belts before seeding our planet. Even more astonishing, the same chemistry might be unfolding right now on frozen moons. Europa's hidden ocean, encased in miles of ice, could harbor similar slow-motion reactions, with cold preserving the very ingredients that warmth might later awaken into life. What makes these frozen zones so special isn't just the cold, it's what the cold allows. Heat agitates, breaks bonds, scatters molecules. Cold gathers, protects, and gives them time. In the emptiness between stars where temperatures plunge, dust grains become tiny laboratories. Ice coats their surfaces, and on these frozen platforms, atoms meet and link in ways impossible elsewhere. It's like nature pressing pause, letting fragile structures build undisturbed until, perhaps, they're ready to play their part in life's grand story. This isn't just about how life began on Earth. It's a universal recipe written in ice and waiting in the dark. The Boomerang Nebula isn't just a cosmic oddity, it's a frozen time capsule. At nearly 272 degrees below zero, it's colder than the natural background chill of space itself. This eerie glow of gas and dust stretching across light years is what astronomers call a protoplanetary nebula, a dying star shedding its outer layers in ghostly whispers. But within this stellar afterlife, something extraordinary is happening. The same cold that would instantly freeze a human solid is preserving delicate chemical structures like formaldehyde and ethanol, molecules we often associate with life's chemistry. These aren't just random compounds floating in the void. They're the raw ingredients for sugars, amino acids, and even the nucleobases that form DNA's twisted ladder. What's astonishing is how these molecular clouds operate like cosmic refrigerators. Picture an ice-covered rock in space, not solid water, but layers of frozen carbon monoxide, methanol, and ammonia. When faint starlight or cosmic rays tickle these icy grains, they trigger reactions so slow they'd be invisible on Earth. A single chemical bond might take centuries to form here. Yet that sluggish pace is precisely what allows more complex structures to emerge. Without the destructive energy of heat, fragile molecular chains can grow uninterrupted, like a fragile crystal forming in perfect stillness. Some of these icy particles eventually clump together, drifting into the warmer embrace of newborn solar systems, possibly delivering life's starter kit to planets like Earth billions of years ago. The implications ripple far beyond our own origins. Right now, telescopes are spotting these same organic molecules in younger nebulae across the galaxy, places where new stars and planets are still taking shape. It suggests this isn't some rare fluke, but a universal process. Every swirling molecular cloud could be a silent factory, assembling life's puzzle pieces in the cold dark. Even more tantalizing, some of these clouds contain molecules like ethyl formate, which gives raspberries their scent. While space doesn't smell like fruit, the presence of such complex organics hints that the universe might be far more chemically inventive than we ever imagined. These nebulas challenge our assumptions about where life could arise. We once thought habitable zones required warmth, the Goldilocks distance from a star. But if complex chemistry thrives in the deepest cold, then frozen moons, rogue planets drifting between stars, or even the dense cores of interstellar clouds might harbor the precursors of life. The Boomerang Nebula and its kin aren't just frigid wastelands. They're the universe's quiet workshops where patience and cold conspire to craft the very things that make planets bloom. Interstellar ice might seem like just frozen water drifting through space, but it's far more extraordinary. It's a cosmic chemistry lab running on deep time. Picture a single dust grain, smaller than a speck of pollen, drifting in the darkness between stars. Over eons, layers of ice cling to its surface, not just water but frozen methane, ammonia, and carbon monoxide. These ices aren't passive frost, they're dynamic shields, protecting fragile molecules from the harsh radiation that would otherwise tear them apart. Inside this frozen shell, something remarkable happens. Atoms and molecules, slowed to a crawl by the cold, begin an achingly slow dance, linking up in ways that warmth would never allow. Scientists have recreated these conditions in labs here on Earth, mimicking the near-absolute zero temperatures of interstellar space. When they blast these artificial ices with radiation simulating the cosmic rays that streak through the galaxy, something astonishing occurs. Simple compounds like hydrogen cyanide or formaldehyde trapped in the ice start rearranging into more complex structures. Over time, they form amino acids, the very building blocks of proteins essential for life. It's as if the universe, in its coldest, quietest corners, is quietly assembling life's toolkit, one frozen grain at a time. This process isn't fast by human standards. A reaction that takes seconds in a warm lab might span millennia in the void, but that's the secret. Time is space's greatest ally. With no heat to disrupt them, delicate molecular chains grow undisturbed, like a spider weaving its web in perfect stillness. Some of these icy grains eventually drift into the warmer embrace of forming solar systems, where heat and liquid water could awaken their dormant chemistry. Imagine comets packed with these preserved organic compounds, delivering them to young planets like Earth billions of years ago. The same ice that seems lifeless might have been the courier that brought life's precursors to our doorstep. What's even more mind-bending is how universal this recipe appears. Telescopes have spotted these icy coatings on dust grains throughout the Milky Way, from the outskirts of star-forming regions to the vast, empty stretches between stellar neighborhoods. It suggests that wherever conditions are cold enough, the universe is running the same slow-motion experiment, stockpiling life's ingredients in frozen vaults, waiting for the right moment to thaw. And it's not just about Earth. If this chemistry works here, why not on icy moons like Europa or Enceladus, where subterranean oceans churn beneath frozen crusts? Or on rogue planets wandering far from any star, where subsurface ice might hide similar molecular treasures? The deeper we look, the more these interstellar ices reveal their hidden potential. They're not just frozen water, they're time capsules preserving the universe's patience and ingenuity. In their silent, cold embrace, the simplest molecules transform into something far more complex, hinting that life's origins might be written not in fire but in ice. Cosmic rays are the universe's invisible sculptors, carving intricate chemistry into the frozen canvas of interstellar ice. These aren't gentle beams of light, they're high-energy particles racing through space at nearly the speed of light, flung from exploding stars or the violent edges of black holes. When one of these particles slams into an icy grain drifting in the void, something extraordinary happens. The impact delivers a burst of energy, like a match struck in a dark room, igniting reactions that would otherwise lie dormant in the deep cold. Simple molecules like water, methane, or ammonia, frozen solid and inert, suddenly awaken, rearranging into more complex structures. It's as if the universe has found a way to whisper to these molecules, nudging them toward the first steps of life's recipe. The magic lies in the balance. Without the extreme cold, these newly formed compounds would shatter instantly, torn apart by the heat of their own reactions. But in the icy stillness, they're preserved, shielded long enough to grow into something more. Experiments here on Earth have recreated this delicate dance. Scientists bombard artificial interstellar ice with radiation, mimicking cosmic rays, and watch as molecules like glycine, the simplest amino acid, emerge from the chaos. These reactions aren't quick or flashy. They're slow, meticulous, and utterly dependent on the cold's protective embrace. Imagine a glassblower working in zero gravity, crafting fragile shapes that would collapse under their own weight anywhere else. That's what cosmic rays and ice accomplish together, a partnership as unlikely as it is essential. What's even more astonishing is how universal this process could be. Cosmic rays aren't rare, they flood every corner of the galaxy, meaning these chemical triggers are everywhere. In the frozen outskirts of a nebula, inside a comet's icy heart, or beneath the surface of a distant moon, the same quiet alchemy could be unfolding. Some researchers speculate that this might explain why we find amino acids in meteorite space rocks that once drifted through these frigid, ray-bathed regions. It's as if the universe has a failsafe, a way to keep life's ingredients simmering even in the most inhospitable places. The implications ripple outward. If cosmic rays and cold can conspire to build life's precursors here, why not elsewhere? Picture a frozen exoplanet far from its star's warmth, bombarded by these high-energy particles. Beneath its icy shell, the same chemistry could be brewing, hidden from view but teeming with potential. Or consider Europa's subsurface ocean, where cosmic rays penetrating the ice might trigger reactions in the dark waters below. This isn't just about how life began, it's a reminder that the universe thrives on collaboration. Cold preserves, cosmic rays energize, and together, they might hold the key to turning stardust into something far more extraordinary. Deep beneath Antarctica's ice, where sunlight never reaches and temperatures plunge far below freezing, life not only survives, it thrives. In lakes buried under miles of glacial ice, where the water hasn't touched open air for millions of years, scientists have discovered bustling communities of microorganisms. These extremophiles, as they're called, endure conditions that would instantly kill most living things, their secret slowing down to almost nothing. With metabolisms running at a fraction of their normal speed, they enter a state akin to suspended animation, conserving energy until rare nutrients drift their way. Some reproduce just once every 100 years, a heartbeat in biological terms, yet proof that life can persist where time itself seems frozen. What's truly remarkable is how these microbes rewrite the rules of survival. Take the permafrost microbes of Siberia, locked in ice for tens of thousands of years. When scientists thaw them, many simply wake up, resuming their lives as if hitting play after a long pause. Others have evolved bizarre adaptations, like proteins that resist freezing or enzymes that function perfectly in the cold. These aren't just curiosities, they're blueprints for how life might endure in the cosmos. If Earth's extremophiles can hack survival in ice that's existed since the last ice age, why couldn't similar organisms arise on Europa, where a saltwater ocean sloshes beneath a crust of ice thicker than Mount Everest? The parallels to space are uncanny. In Antarctica's dry valleys, one of Earth's most Mars-like environments, microbes survive not by clinging to warmth, but by embracing the cold. They nestle inside porous rocks, where microscopic pockets of liquid water persist even at -60 degrees. It's a stark reminder that life doesn't always need tropical temperatures, just a tiny refuge where chemistry can inch forward. Astronomers now suspect similar microhabitats could exist on icy moons or even in the frozen regolith of asteroids. Perhaps the most tantalizing clue comes from Earth's cryopeg's briny pockets trapped in Arctic permafrost, so salty they remain liquid at -10 degrees. Here, communities of bacteria thrive in isolation, cut off from the surface for millennia. Their existence mirrors what might lurk in Enceladus' subsurface ocean, where hydrothermal vents could melt icy ceilings, creating pockets of warmth in an otherwise frozen world. These Earth-bound extremophiles are more than survivors. They're messengers showing us that life's playbook is far more flexible than we ever imagined. The lesson is clear: cold isn't necessarily life's enemy. It can be a preservative, a stabilizer, even a catalyst for chemistry that warmth would disrupt. If life on Earth has mastered the art of living slowly in the ice, then the universe's frozen frontiers might not be barren after all. They could be hibernating gardens, waiting for the right conditions to bloom. Every new extremophile discovered in Earth's icy wastes expands the boundaries of where we might find life beyond our planet. The cold, it seems, doesn't extinguish life's flame, it just teaches it to burn differently. Panspermia turns the universe into a grand conveyor belt for life, one where ice acts as both protector and vehicle. Imagine a microscopic organism frozen solid inside a comet, hurtling through space for millions of years. Shielded from radiation by layers of ice and sheltered from the vacuum's extremes, it remains in suspended animation until a chance encounter with a warm, watery world. This isn't science fiction. We've already found hardy earthly microbes that survive simulated space conditions, and comets like 67P/Churyumov-Gerasimenko contain complex organic molecules. If life's ingredients can endure such journeys, the coldest reaches of space might not just cradle life's origins, they could be its interstellar highways. The math is startlingly plausible. A single cubic meter of comet ice could harbor billions of microbial hitchhikers, preserved like insects in amber. When that comet collides with a planet, the heat of impact could melt its frozen cargo, releasing those dormant passengers into a new environment. Experiments show some bacteria, like Deinococcus radiodurans, can withstand cosmic radiation for years, especially when embedded in ice. Even if most perish, the sheer number of icy bodies traveling between stars makes the odds staggering. A single surviving microbe landing in the right puddle at the right time could rewrite an entire world's history. But panspermia isn't just about living organisms. The icy asteroids and comets drifting through our solar system are cosmic pharmacies packed with prebiotic chemicals. Take the Murchison meteorite, which crashed in Australia in 1969. Inside its frozen fragments, scientists found over 90 amino acids, many not even present on Earth. These weren't contaminants, they were extraterrestrial, forged in the cold depths of space and delivered intact. If such complex chemistry can survive the violent trip through our atmosphere, imagine what might arrive gently, embedded in the ice of a slow-moving comet. The implications stretch beyond our solar system. Rogue planets' worlds flung from their stars during cosmic collisions might outnumber stars in our galaxy. Many could be icy, with subsurface oceans kept liquid by geothermal heat. If panspermia is real, these drifting nomads could be transporting life between star systems, frozen in time until they pass near a new sun. Even more mind-bending, some calculations suggest ice-covered ejecta from Earth's ancient meteor strikes might have carried terrestrial microbes to Europa or Enceladus. Life might not just spread from the cosmos to us, we could be part of the delivery network too. What makes this theory so compelling is its duality. The coldest places in the universe aren't just where life's building blocks form, they're also the freezers that keep them fresh for delivery. Ice isn't a barrier, it's a bridge spanning light years and epochs. Whether through comets, asteroids, or wandering planets, the same frigid conditions that seem inhospitable might be the universe's way of ensuring life gets a ride. Comets are more than just spectacular streaks across the night sky. They're cosmic time capsules, frozen vaults carrying the raw ingredients of life across the solar system. These icy wanderers, born from the same swirling cloud of gas and dust that formed our sun and planets, have spent billions of years drifting in the deep freeze of space. Locked within their cores are organic molecules like formaldehyde, hydrogen cyanide, and even amino acids, preserved in pristine condition by temperatures nearing absolute zero. When a comet swings close to the sun, its surface erupts in jets of gas and dust, offering scientists a glimpse of the chemistry hidden beneath its icy shell. The European Space Agency's Rosetta mission witnessed this firsthand when it orbited Comet 67P, detecting glycine, a fundamental building block of proteins floating in the comet's hazy coma. This discovery wasn't just a lucky find, it was confirmation of a revolutionary idea. Comets might be the universe's delivery system, ferrying life's precursors from the frigid outer solar system to warmer, water-rich worlds like early Earth. Picture a young planet still cooling from its violent formation, bombarded by icy comets. Each impact melts frozen organics, releasing them into primordial ponds or hydrothermal vents. Over time, these molecules could link up, forming more complex structures like peptides or RNA. It's a scenario supported by lab experiments, where simulating comet impacts in water produces amino acids and even nucleotide bases, the very letters of life's genetic code. But comets don't just deliver ingredients, they protect them. In the vacuum of space, radiation would shred fragile organic molecules within centuries. Yet encased in ice, those same compounds survive for eons. The ice acts like a molecular shield, absorbing harmful energy while allowing slow, cold-driven chemistry to unfold. Some comets even contain clathrates, crystalline cages of water molecules that trap gases like methane or carbon dioxide. These structures could serve as tiny reaction chambers, concentrating organics and fostering reactions that might lead to greater complexity. The implications stretch far beyond Earth. If comets seeded our planet, why not others? Mars, once wet and warm, was likely pummeled by the same cometary hailstorm as Earth. Even today, its polar ice caps and subsurface glaciers could harbor preserved organic payloads from ancient impacts. And what of icy moons like Europa or Enceladus? Their subsurface oceans might be enriched by cometary deliveries, creating hidden reservoirs of probiotic chemistry. The universe, it seems, has a habit of packaging life's blueprints in ice and sending them on celestial journeys. Perhaps most astonishing is the sheer abundance of these icy messengers. The Oort Cloud, a vast shell of comets surrounding our solar system, may hold trillions of them. Each one a potential ark, carrying not just water and simple organics, but increasingly complex molecules we're only beginning to identify. Recent studies of comet atmospheres have detected sugars like ribose, a key component of RNA, and even alcohol molecules. This isn't just chemistry, it's a cosmic pantry stocked with the very ingredients that, under the right conditions, could stir to life. The next time you see a comet's tail stretching across the sky, remember, you're not just witnessing a space rock vaporizing in the sun's heat. You're looking at a deep freeze delivery from the solar system's infancy, a reminder that the coldest places in space might hold the warmest secrets of life's origins. Far beyond the warmth of any star, in the silent outskirts of distant solar systems, a new class of worlds defies expectations: exoplanets locked in eternal frost. These aren't the barren, airless wastelands we once imagined. Take, for example, the enigmatic planet K2-18b, orbiting a dim red dwarf over 100 light-years away. Its surface temperature hovers around -200 degrees Celsius, cold enough to freeze nitrogen solid. Yet, beneath miles of ice, tidal forces from its star and radioactive decay in its core might maintain vast liquid oceans, hidden from view but teeming with potential. The mechanics of these frozen oases are as elegant as they are unlikely. On Earth, geothermal vents at the bottom of our oceans support entire ecosystems without a single ray of sunlight. Now picture that same process scaled across a planet where the surface ice is thicker than Earth's crust. Heat from the planet's molten core rises, melting the base of the ice shell, creating a global aquifer of liquid water. Chemical nutrients seeping up from hydrothermal systems below could sustain microbial life, or even more complex organisms adapted to the slow rhythms of a sunless world. Astrobiologists call these worlds frost zone exoplanets, and they're rewriting the rules of habitability. Traditional definitions demanded planets orbit in the Goldilocks zone, not too hot, not too cold. But what if life doesn't need a star's warmth at all? Europa and Enceladus in our solar system already hint at this possibility. Now, telescopes like JWST are spotting similar candidates among the stars. The exoplanet LHS 1140b, for instance, is a frozen super-Earth with an atmosphere that might contain water vapor, a clue that geothermal heat could be maintaining liquid reservoirs beneath its icy surface. The implications are staggering. If life can emerge and persist in these lightless abysses, then the universe's habitable real estate just expanded exponentially. Rogue planets untethered from any star and drifting through interstellar space might host similar subsurface oceans, warmed only by their internal heat. Even more intriguing, the chemistry in these isolated oceans could evolve in radically different directions than Earth's sunlit biosphere. Without photosynthesis, organisms might harness chemical energy from hydrothermal vents, or even the faint radioactive decay in the rocks below. What makes these frost zone worlds so compelling isn't just their potential to host life, it's how they challenge our assumptions. Life as we know it requires liquid water, but not necessarily sunlight. Stability matters more than warmth. An ice shell 10 miles thick might seem like a prison, but it's also a shield protecting delicate ecosystems from cosmic radiation and asteroid impacts. In the endless cold between stars, these hidden oceans could be the ultimate refuges, where life persists for billions of years, unchanging and undisturbed. The search for these frozen worlds is accelerating. Next-generation telescopes will probe their atmospheres for traces of methane or molecular oxygen, gases that, in the absence of sunlight, could signal biological activity. Meanwhile, missions like Europa Clipper will test our models by exploring the closest analogs in our own solar system. Every discovery pushes the boundaries of where we imagine life could thrive. The universe's coldest planets might not be dead ends. They could be dark gardens waiting patiently in the freeze. Dark matter doesn't just weave the unseen scaffolding of the cosmos, it might also be silently shaping the universe's coldest corners. This mysterious substance, making up roughly 85% of all matter in existence, doesn't interact with light or ordinary atoms the way stars and planets do. Yet its gravitational pull is what keeps galaxies from flying apart. Now, researchers are exploring a tantalizing possibility. Could dark matter's subtle interactions create microscopic pockets of extreme cold, colder than even the void of space itself? The idea hinges on a peculiar property of certain dark matter candidates, like weakly interacting massive particles, WIMP for short. If these particles occasionally collide and annihilate one another, they could release energy in the form of heat. But in regions where dark matter is dense and motionless, the opposite might occur. Imagine a cloud of dark matter particles drifting through a nebula. If they interact just right, they could siphon away thermal energy from ordinary matter, cooling their surroundings to temperatures we've never measured naturally. It's like a cosmic air conditioner, silently dialing down the heat in isolated patches of the universe. This isn't just theoretical. In 2017, astronomers studying a bizarrely cold gas cloud in the Musca constellation found it couldn't be explained by known physics alone. The cloud's temperature was a fraction of what models predicted, almost as if something invisible were leaching away its warmth. While the findings are still debated, they've sparked a provocative question: could dark matter be the culprit? If so, these ultra-cold zones might be more than curiosities. They could be petri dishes for chemistry that can't happen elsewhere, where molecules form at speeds so glacial they'd be impossible in warmer, more chaotic environments. Consider what that means for life's building blocks. In ordinary space, complex organic molecules are fragile. They break apart almost as quickly as they form. But in a dark matter-chilled pocket, reactions could unfold with precision, like a watchmaker assembling gears in slow motion. Amino acids, sugars, or even nucleobases might link up undisturbed, shielded from the usual cosmic turmoil. Some scientists speculate that these hidden cold spots could be where the universe's first self-replicating molecules emerged, preserved like insects in amber until they drifted into a warmer, more hospitable environment. The implications ripple outward. If dark matter can sculpt temperature extremes, then the coldest places in the universe might not be random. They could be deliberate engineered by the invisible hand of dark matter's peculiar physics. That changes how we search for life's origins. Instead of only scanning warm, watery worlds, we might need to look for the fingerprints of dark matter's chill in distant molecular clouds or the frozen outskirts of planetary systems. Perhaps most mind-bending is the timescale. Dark matter has existed since the universe's infancy, meaning these icy pockets could have been operating for billions of years, quietly assembling life's ingredients in the dark. It's a humbling thought. The same mysterious substance that binds galaxies might also be a silent architect of life's blueprint, working in the cold and the quiet, where no telescope can yet see. At temperatures just a whisper above absolute zero, the ordinary rules of physics dissolve, and the bizarre world of quantum mechanics takes over. Here, particles defy common sense, existing in multiple places at once or spinning in opposite directions simultaneously. It's a realm where matter behaves less like solid stuff and more like probability waves, flickering between possibilities until observed. But what if life itself has learned to harness these quantum quirks? A growing field called quantum biology suggests that evolution might have tapped into these phenomena, especially in environments where cold preserves delicate quantum states far longer than they'd survive in warmth. Consider photosynthesis, the process plants use to turn sunlight into energy. At room temperature, it seems straightforward, but zoom in to the molecular level and something astonishing emerges. Experiments show that energy in photosynthetic systems doesn't travel in a straight line. Instead, it spreads out like ripples in a pond, exploring multiple paths at once before settling on the most efficient route. This isn't just random motion. It's a quantum effect called coherence, where particles act as waves to test all possible routes simultaneously. In the icy depths of space, where cold suppresses disruptive thermal noise, similar quantum tricks could help molecules find optimal configurations for life's chemistry. The connection gets even stranger when you examine enzymes, biological catalysts that speed up chemical reactions. Some researchers propose that enzymes work by leveraging quantum tunneling, where particles magically bypass energy barriers instead of climbing over them. In warm environments, this effect is fleeting, but in the deep cold of interstellar ice or frozen moons, quantum tunneling could become life's secret shortcut, allowing reactions to occur that would otherwise be impossibly slow. Imagine a key unlocking a door not by turning, but by phasing straight through the lock. That's the kind of efficiency quantum biology suggests life might exploit in extreme cold. The implications ripple outward. If quantum effects play a role in life's basic processes, then the coldest places in the universe might be ideal laboratories for life's origins. In the near-perfect stillness of a molecular cloud, where temperatures hover a few degrees above absolute zero, quantum coherence could help complex molecules self-assemble with precision. It's like nature running a billion tiny experiments at once, letting quantum probabilities guide the way until the right combinations emerge. Some theorists even speculate that the first self-replicating molecules, life's precursors, might have relied on these quantum shortcuts to overcome the odds. This isn't just speculation. Experiments with ultra-cold quantum systems show that molecules can form bonds in ways classical chemistry can't explain. In 2018, scientists observed quantum entanglement, a phenomenon where particles remain mysteriously linked across distances in molecules at temperatures cold enough to mimic space. If entanglement can persist in these conditions, it raises a provocative question. Could life's earliest chemical reactions have been coordinated by quantum connections we're only beginning to understand? The coldest corners of the cosmos might hold the answer. On frozen moons like Europa, where tidal forces create liquid water beneath miles of ice, quantum effects could be quietly shaping biochemistry in ways we've never imagined. Or in the drifting comets between stars, where ice preserves delicate quantum states for eons, even Earth's extremophiles thriving in ice-bound lakes might owe their resilience to subtle quantum adaptations. The universe's deep freeze isn't just a preservative, it could be the stage where life's quantum dance first began. Astrobiologists have turned Earth's most unforgiving landscapes into living laboratories, uncovering organisms that thrive where nothing should survive. Take Lake Vostok, buried beneath 2.5 miles of Antarctic ice, untouched by sunlight for 15 million years. When scientists finally drilled through to its waters, they found bacteria not just enduring but flourishing in the pitch-black cold. These microbes don't rely on photosynthesis or organic debris from the surface. Instead, they've hacked chemistry itself, extracting energy from hydrogen and sulfur compounds seeping up from geothermal vents below. Their existence proves life doesn't need warmth or light, just a trickle of energy and a molecule to metabolize. This revelation shatters old assumptions about habitable zones. If microbes can subsist in a frozen lake isolated for epochs, why not in Europa's subsurface ocean, where tidal forces keep water liquid beneath an icy crust? Or in the methane lakes of Titan, where temperatures plunge to -180 degrees Celsius? Earth's extremophiles are more than curiosities, they're roadmaps, pointing us toward the most likely hideouts for life beyond our planet. Consider the Atacama Desert, the driest place on Earth, where bacteria cling to life inside salt rocks, absorbing minuscule traces of nighttime humidity. Now imagine similar tenacity on Mars, where briny streaks might still seep to the surface, or in the icy fractures of Enceladus's plumes, where microbial hitchhikers could ride geysers into space. The coldest environments teach us something profound. Life isn't fragile, it's stubborn. In Siberian permafrost, scientists revived bacteria frozen for 24,000 years, organisms that simply hit pause on metabolism until conditions improved. On Earth, we call them extremophiles. In space, they might be the norm. The same cold that preserves ancient viruses in glaciers could safeguard microbial communities in the subsurface oceans of distant moons, where geothermal heat and chemical gradients create oases in the freeze. Astrobiology's coldest case isn't just about finding life where we expect it, it's about redefining what's possible. Every time we discover organisms thriving in Earth's icy extremes, the universe's frozen frontiers feel a little less hostile. From the salt-loving halophiles of Antarctica's dry valleys to the pressure-resistant microbes lurking in the Mariana Trench, these Earth-bound survivors whisper a tantalizing promise. If life can adapt here, it could be hiding anywhere. The coldest corners of space aren't dead ends, they're waiting to be unlocked. The Murchison meteorite didn't just crash into Australia in 1969. It shattered our understanding of life's cosmic ingredients. Inside this charred space rock, scientists found a treasure trove of organic compounds, from simple amino acids to complex molecules like uracil, a building block of RNA. What makes Murchison extraordinary isn't just what it contains, but how pristine these molecules remain, locked in icy stasis for over 4.5 billion years. This isn't an isolated case. Across the globe, similar meteorites reveal the same startling pattern: frozen pockets of chemistry that mirror the precursors of life on Earth. These space rocks act as cosmic deep freezers, preserving delicate organic material against the ravages of time. Unlike Earth's dynamic surface, where heat and erosion constantly reshape the landscape, asteroids, the parent bodies of most meteorites, exist in a near-perfect cryogenic state. Temperatures in the asteroid belt rarely climb above -100 degrees Celsius, creating an environment where even the most fragile molecular structures survive unscathed. When fragments break loose and plummet to Earth, they deliver these ancient chemicals like a time machine in a rock. But the real revelation lies in the diversity of these compounds. The Tagish Lake meteorite, which fell over Canada in 2000, contained organic material so complex it defied easy categorization. Some molecules resembled the fatty acids that form cell membranes, while others mirrored the aromatic hydrocarbons found in coal. This isn't random contamination. It's evidence of a sophisticated chemical factory operating in the early solar system, one that didn't just produce simple ingredients but an entire toolkit of potential life starters. Lab experiments now show how these molecules might have formed. In simulated interstellar ices, scientists recreate the cold vacuum of space, bombarding frozen mixtures of water, ammonia, and methanol with ultraviolet light. Over time, these simple ingredients rearrange into amino acids and nucleobases, the same compounds found in meteorites. The process isn't fast by human standards, but given millions of years in a quiet corner of a nebula or asteroid, the results are astonishing. Perhaps most intriguing is what these fossils suggest about delivery. When Earth was young and still pummeled by impacts, icy asteroids and comets could have seeded our planet with these preserved organics. The heat of entry wouldn't necessarily destroy them. Some amino acids withstand temperatures over 300 degrees Celsius. Once lodged in warm ponds or hydrothermal vents, these molecules might have kick-started the next phase of chemical evolution, assembling into more complex structures like peptides or RNA strands. The implications reach far beyond our own origins. If meteorites carried life's precursors to Earth, why not elsewhere? Mars, with its ancient lakes and rivers, likely received similar deliveries. Even Venus, before its greenhouse effect ran wild, might have been a recipient. And beyond our solar system, exoplanets orbiting red dwarfs, where icy bodies are plentiful, could have undergone the same process. The universe, it seems, has a habit of packaging life's raw materials in frozen rock and sending them on celestial journeys. Every meteorite that survives the plunge through our atmosphere is more than a scientific curiosity. It's a messenger from the deep past, whispering secrets about how stardust transforms into the building blocks of biology. As we analyze more of these cosmic fragments, we're not just piecing together Earth's history. We're decoding a universal recipe written in ice and stone, waiting to be read. Enceladus isn't just another frozen moon. It's a cosmic fountain, erupting with secrets from the ocean hidden beneath its icy shell. Every second, towering geysers blast water vapor and ice crystals hundreds of miles into space, creating Saturn's faint E-ring. But when NASA Cassini spacecraft flew through these plumes, it didn't just find water. The probe detected a cocktail of organic molecules, from methane and carbon dioxide to more complex compounds like formaldehyde and hydrogen cyanide. These aren't just random chemicals. They're the raw ingredients for amino acids, the building blocks of proteins essential for life. What makes Enceladus extraordinary isn't just what it's spraying into space, it's what these geysers imply about the warm, salty ocean lurking below. Beneath 25 miles of ice, Enceladus hides a global sea, kept liquid by the Moon's constant gravitational tug of war with Saturn. This isn't some stagnant pool. Hydrothermal vents likely churn on the seafloor, spewing mineral-rich fluids into the water. On Earth, similar vents teem with extremophiles, organisms that thrive in scorching, chemical-laden environments. If life exists on Enceladus, it might cling to these underwater chimneys, drawing energy from chemical reactions rather than sunlight. The geysers offer a tantalizing clue. Their plumes contain molecular hydrogen, a gas that, on our planet, often signals microbial activity deep underground. But Enceladus isn't alone in its icy intrigue. Europa, Jupiter's enigmatic moon, boasts a subsurface ocean twice the volume of Earth's seas, capped by a cracked, shifting ice shell. Then there's Titan, Saturn's largest moon, where rivers of liquid methane carve valleys into frozen hydrocarbon dunes. Even distant Triton, Neptune's captured icy world, erupts with nitrogen geysers. Each of these moons suggests a universal truth. Where there's ice and energy, the potential for life follows. The implications are staggering. If Enceladus's ocean hosts even simple microbes, it proves life isn't a fluke confined to Earth. It's a cosmic inevitability, arising wherever conditions allow. Future missions, like the proposed Enceladus Life Finder, could analyze these plumes for amino acids or lipids, molecules that would scream biology to scientists. And if we find nothing that's equally profound, it would mean the universe's recipe for life requires more than just water and organics. It needs a secret ingredient we've yet to uncover. Either way, these icy moons are more than frozen rocks. They're the universe's way of testing its own limits, proving that even in the coldest dark, life finds a way. Europa glows faintly in Jupiter's shadow, its cracked icy shell gleaming like a shattered mirror under the gas giant's relentless pull. Beneath this frozen facade lies one of the solar system's most tantalizing secrets, a global ocean with more than twice the volume of all Earth's seas combined. Unlike our planet's surface-dominant waters, Europa's ocean is sealed under miles of ice, a hidden realm where sunlight never penetrates. Yet here, in this lightless abyss, Jupiter's gravity works its magic. The colossal tidal forces stretching and compressing Europa's core generate enough heat to keep the water liquid, and possibly even fuel hydrothermal vents spewing mineral-rich plumes into the dark. On Earth, such vents are oases of life. In the crushing depths of the Atlantic, whole ecosystems thrive around these underwater geysers, sustained not by photosynthesis but by chemosynthesis, bacteria converting sulfur and methane into energy. The parallels are irresistible. If life can flourish around Earth's vents, why not Europa's? The Moon's ocean likely interacts with a rocky seafloor, leaching minerals and creating chemical gradients that could fuel alien microorganisms. Even more compelling, Europa's icy crust isn't static. Images from spacecraft like Galileo reveal chaotic terrain where ice blocks have clearly shifted, suggesting occasional meltwater pockets or lakes suspended within the shell. These could be mixing zones where surface chemicals like oxygen, created when radiation splits water molecules, percolate downward, potentially supplying nutrients to the ocean below. The surface itself tells a story of dynamism. Europa's fractures, stained reddish-brown by salts and organic compounds, resemble the cracks in Arctic sea ice. Some scientists speculate these discolorations could be cryovolcanic residue evidence of briny water erupting through the ice and freezing instantly in the vacuum of space. The Hubble Space Telescope has even spotted transient water vapor plumes near Europa's south pole, echoing Enceladus's famous geysers. If confirmed, these plumes would offer a golden opportunity. Future missions could fly through them, sampling Europa's ocean without drilling through miles of ice. What truly sets Europa apart is time. While Mars dried up and Venus broiled, Europa's ocean has likely persisted for billions of years, a stable if strange habitat. Imagine a world where the only sun is the dim glow of hydrothermal vents, where life evolves in slow motion under the weight of ice, adapting to pressures that would crush a submarine. Organisms here might resemble Earth's most resilient extremophiles, like the bacteria found in Lake Vostok, surviving on chemical energy alone. Or they could be something entirely alien, leveraging Europa's unique chemistry, perhaps using hydrogen peroxide detected on the surface as an energy source. The upcoming Europa Clipper mission, set to launch in 2024, could rewrite the textbooks. Armed with ice-penetrating radar and chemical analyzers, it will map the ocean's depth, salinity, and even potential hotspots of activity. If Clipper finds evidence of present-day vents or organic complexity, the implications would echo far beyond Jupiter. It would mean that life isn't just possible in the cosmos, it's probable, hiding in the dark, warmed not by starlight but by the silent flex of gravity. Europa's ice might seem like a barrier, but it's also a shield, preserving a world where the rules of biology could be rewritten in the deep. Titan isn't just Saturn's largest moon. It's a looking-glass world where familiar substances behave in utterly alien ways. Here, at a bone-chilling -180 degrees Celsius, methane takes on the role water plays on Earth, pooling into vast lakes and carving river valleys through icy bedrock. Nitrogen rains from hazy orange skies, and dunes of hydrocarbon sand stretch for miles. It's a landscape both eerily familiar and profoundly strange, like a distorted reflection of our own planet. But beneath the surreal scenery lies an even more tantalizing question. Could this frigid, methane-soaked world harbor life? Not life as we know it, but something entirely new, organisms built from exotic chemistry, thriving in conditions that would instantly freeze or vaporize earthly creatures. The possibility hinges on Titan's liquid methane and ethane, which replace water as solvents in potential biochemical reactions. On Earth, water's unique properties, its ability to dissolve nutrients, facilitate molecular interactions, and maintain cellular structures, make it essential for life. But what if methane could serve a similar purpose in Titan's deep freeze? Scientists like Chris McKay have theorized about methane-based life forms that use acetylene instead of glucose for energy, breathing hydrogen gas instead of oxygen. These hypothetical organisms would metabolize at a glacial pace, their chemical reactions slowed by the extreme cold, yet still capable of growth, reproduction, and evolution over Titan's billion-year history. Evidence for this wild idea comes from Titan's dynamic environment. The Cassini spacecraft mapped lakes as deep as 300 feet, with shorelines shaped by tides and waves. Seasonal changes cause methane clouds to form and dissipate, while underground reservoirs may feed cryovolcanoes spewing slushy ice. This active cycle of evaporation, precipitation, and erosion mirrors Earth's water cycle, suggesting Titan's chemistry is anything but stagnant. Even more intriguing are the Moon's magic islands, transient bright spots in its seas that could be floating clumps of organic solids or even, hypothetically, microbial mats buoyed by methane bubbles. Laboratory experiments add weight to these speculations. When researchers simulate Titan's conditions, mixing nitrogen, methane, and energy sources like ultraviolet light, complex organic molecules called tholins form spontaneously. These compounds, which give Titan its orange haze, include amino acids and nucleotide bases, the same building blocks that, on Earth, led to life. While no one has yet created a self-replicating methane-based organism in the lab, the fact that such chemistry occurs at all hints at Titan's potential. The implications stretch beyond a single moon. If life can arise in Titan's methane lakes, then hydrocarbon solvents might be viable alternatives to water across the cosmos. Exoplanets with thick atmospheres and cold temperatures, super-Earths orbiting red dwarfs, or rogue planets drifting between stars, could host similar ecosystems. Titan becomes a test case, proving that life's template might be far more flexible than we ever imagined. Future missions like NASA's Dragonfly drone will explore Titan's surface in the 2030-50s, sampling its organic-rich dunes and possibly even skimming the edges of its methane seas. What they find could rewrite biology itself. Whether Titan harbors life or not, its existence challenges us to think bigger, to envision a universe where biology isn't limited to Earth's cozy conditions, but flourishes in the unlikeliest places, rewriting the rules of existence in the process. Pluto's heart isn't just a charming quirk, it's a frozen engine pulsing with secrets that defy expectations. This distant world, once dismissed as a lifeless ice ball, reveals a landscape of staggering complexity beneath its nitrogen ice plains. The heart-shaped feature known as Tombaugh Regio isn't static. It's a glacier in slow motion, flowing like toothpaste squeezed from a tube under Pluto's feeble sunlight. Nitrogen, carbon monoxide, and methane ices creep across the surface, sculpting valleys and ridges in a dance that reshapes the terrain over millennia. What keeps this frozen heart beating? Residual heat from radioactive decay in Pluto's rocky core, combined with the faint warmth of tidal interactions with its largest moon, Charon. Even here at the solar system's edge, energy persists, and where there's energy, the door to possibility cracks open. Beneath Sputnik Planitia, the western lobe of the heart, lies something even more intriguing, a subsurface ocean kept liquid by ammonia acting as cosmic antifreeze. This isn't pure speculation. Pluto's lack of surface fractures suggests a layer of slushy water buffers its icy shell from the rocky core. If confirmed, it would mirror the hidden oceans of Europa and Enceladus, proving that liquid water isn't confined to the inner solar system. The implications are profound. While Pluto's surface is far too cold for Earth-like life, hovering around -230 degrees Celsius, its underground sea could theoretically host extremophiles adapted to darkness and cold, much like Antarctica's Lake Vostok microbes. The chemistry here is stranger still. Pluto's reddish-brown haze, captured stunningly by New Horizons, isn't just for show. It's a cocktail of tholins complex organic molecules formed when methane and nitrogen react under sunlight. These compounds rain onto the surface, staining the ice with the same precursors that might have seeded life on early Earth. Some scientists speculate that over billions of years, these organics could seep downward, enriching any subsurface liquid layers with life's raw ingredients. It's a slow-motion delivery system, colder and darker than anything on Earth, yet eerily reminiscent of how comets may have ferried organics to our own planet. What makes Pluto's heart so compelling isn't just its geology, it's the way it challenges our assumptions. A world this distant shouldn't be geologically active. Yet New Horizons spotted ice volcanoes, towering mountain ranges of water ice, and even evidence of recent resurfacing. If Pluto, with its scant sunlight and meager energy budget, can sustain such dynamism, what does that say about the thousands of similar dwarf planets in the Kuiper belt? Or the rogue planets drifting between stars, untethered to any sun? The universe's coldest realms might not be the static graveyards we once imagined, but slow-motion workshops, patiently assembling the pieces of life's puzzle in the dark. The next time you gaze at Pluto's heart, remember, it's not just a symbol of cosmic affection. It's a reminder that even in the deepest freeze, the universe refuses to sit still. Whether life could exist there remains an open question, but the mere possibility rewrites the rules of where and how we should search for it. In Pluto's quiet, frozen whispers, we hear the echo of a broader truth. Life's potential is as boundless as the cold itself. The Oort Cloud is the solar system's final frontier, a vast, dark halo of icy remnants stretching nearly a light year from the Sun, where temperatures hover just a few degrees above absolute zero. Unlike the asteroid belt or Kuiper belt, this distant reservoir isn't flat or compact. It's a spherical shell, a cosmic freezer packed with trillions of frozen bodies, some as small as dust grains, others rivaling mountains. These aren't just random chunks of ice, they're time capsules from the solar system's infancy, preserved in pristine condition for over 4.5 billion years. While Pluto feels remote, the Oort Cloud is another order of magnitude farther out, so distant that the Sun appears as little more than a particularly bright star. What makes these icy wanderers so special is their isolation. Shielded from the heat and radiation that shaped the inner solar system, Oort Cloud objects remain chemically unchanged since their formation. Comets like Hale-Bopp, which likely originated here, contain some of the most complex organic molecules ever detected in space. Compounds like glycolaldehyde, a simple sugar, and methyl formate, which plays a role in prebiotic chemistry. These molecules didn't form in the Oort Cloud itself. They were forged in the turbulent nursery of the early solar system, then flung to the deep freeze by gravitational interactions with Jupiter or Saturn. Out here in the quiet dark, they've waited undisturbed for epochs. The implications are staggering. If a single Oort Cloud comet like Hale-Bopp can carry such a rich cargo of organics, imagine what else might lurk in this frozen archive. Some researchers speculate that interstellar visitors like Oumuamua, the mysterious pancake-shaped object spotted in 2017, could be Oort Cloud analogues from other star systems, carrying chemistry unique to their origins. Even more tantalizing, the Oort Cloud might be the ultimate backup drive for life's building blocks. During the solar system's chaotic youth, countless icy bodies were ejected entirely, becoming rogue comets drifting between stars. If just one of these frozen nomads carried even dormant microbial life, it could have seeded another world light years away. Yet studying the Oort Cloud directly remains a monumental challenge. No spacecraft has ever reached it. Voyager 1, the farthest human-made object, won't enter its outskirts for another 300 years. For now, we rely on rare comets that get knocked inward by passing stars or galactic tides. Each time one streaks through the inner solar system, it's like receiving a message in a bottle from the distant past, written in ice and vapor. Future telescopes, like the Vera Rubin Observatory, may spot more of these primordial messengers, revealing whether the Oort Cloud's chemistry differs from comets born closer to the Sun. The Oort Cloud isn't just a relic. It's a reminder that the solar system's coldest, darkest reaches might be its most chemically inventive. While planets like Earth transformed over eons, these frozen wanderers stayed pure, holding onto secrets we're only beginning to decode. They whisper a provocative idea: life's ingredients aren't rare or fragile. They're scattered across the cosmos, preserved in ice, waiting for the right conditions to awaken. Black holes aren't just cosmic vacuum cleaners, they're also some of the universe's most unexpected refrigerators. Near the edges of supermassive black holes, where gravity bends space into a swirling maelstrom, temperatures can plummet to near absolute zero despite the chaos. It sounds impossible. How can the most destructive objects in existence also create pockets of extreme cold? The answer lies in radiation pressure. As matter spirals toward the event horizon, it heats up to millions of degrees, emitting torrents of X-rays and ultraviolet light. This radiation doesn't just blast outward, it pushes against incoming gas and dust, creating vast, low-density regions where heat dissipates faster than it can accumulate. The result, cosmic cold spots so intense they rival the chill of interstellar space. These frigid zones aren't just curiosities, they're potential laboratories for life's most delicate chemistry. In the shadow of a black hole's accretion disk, shielded from the brunt of radiation, complex molecules like polycyclic aromatic hydrocarbons (PAH) can form and survive. On Earth, pHs are found in everything from engine soot to meteorites, but in the cold near a black hole, they might behave differently. Simulations suggest these molecules could link into longer chains, eventually forming the backbone of more complex organics. Even water, frozen into icy mantles on dust grains, could persist here, protected from evaporation by the very radiation that creates the cold. The real surprise comes when you consider time dilation, Einstein's prediction that time slows near massive objects. Near a black hole, chemical reactions that would take millennia elsewhere could unfold in what appears, to an outside observer, as mere years. This time-stretching effect might allow reactions too slow to be meaningful elsewhere to proceed at a usable pace, giving fragile prebiotic compounds the chance to assemble into something more. It's like nature hitting the slow-motion button, turning a chaotic environment into a controlled experiment. Could life itself emerge in such a hostile place? Probably not as we know it, but the precursors, those first stirrings of complexity, might find these cold pockets oddly hospitable. Some astrobiologists speculate that the organic-rich disks around black holes could seed nearby star systems, much like comets may have done for Earth. Others imagine even wilder possibilities: microbial life clinging to icy debris in the black hole's gravitational grip, metabolizing at a glacial pace, sustained by the faint energy gradients in the cold. The paradox is striking. Black holes, the ultimate destroyers, might also be cosmic midwives, fostering the very chemistry that leads to life. It's a reminder that the universe thrives on contradiction, and that the coldest places to hide life's blueprint might be the last ones we'd think to look. Inside laboratories on Earth, scientists dial down temperatures to levels that mimic the void of space, creating artificial environments where atoms move at a near standstill. Using specialized cryogenic chambers, they plunge samples to just a fraction of a degree above absolute zero, colder than the Boomerang Nebula or the darkest reaches of the Oort Cloud. These aren't just feats of engineering, they're windows into how the universe's most fragile molecules might assemble themselves in the extreme cold. When researchers introduce simple chemicals like water, methane, or ammonia into these frigid chambers and blast them with radiation to simulate cosmic rays, something remarkable happens. Over days or weeks, new compounds emerge: amino acids, sugars, and even nucleobases, the very letters of life's genetic code. One groundbreaking experiment at NASA, a jet propulsion laboratory, recreated the icy surface of Europa in a vacuum chamber no larger than a shoebox. By freezing water mixed with salts and bombarding it with electrons to mimic Jupiter's radiation belts, the team watched as complex organic molecules formed spontaneously. The cold didn't inhibit the chemistry, it refined it. Without the disruptive energy of heat, delicate molecular chains grew undisturbed, like crystals forming in perfect stillness. Similar studies in Germany and Japan have produced ribose, the sugar backbone of RNA, from icy mixtures exposed to ultraviolet light. These lab-grown reactions unfold thousands of times slower than their room temperature counterparts, yet that sluggish pace is precisely what allows complexity to arise. The implications stretch far beyond test tubes. In nature, these same reactions might play out over millennia on frozen dust grains drifting between stars. Lab experiments suggest that the universe's coldest regions could function as molecular factories, where patience and cold collaborate to build life's precursors one bond at a time. Some researchers even propose that the first self-replicating molecules, life's earliest ancestors, might have relied on this slow-motion chemistry, protected by ice until they were ready for warmer, more dynamic environments. What makes these experiments so revealing isn't just the molecules they produce, it's the unexpected efficiency of the process. In warmth, complex organics often break apart faster than they form. But in the deep freeze, every successful bond persists, accumulating like snowflakes in a storm. A single icy grain in space might harbor dozens of these compounds, waiting for a chance encounter with liquid water or geothermal heat to awaken their potential. The coldest labs on Earth are teaching us that the universe's harshest environments might be its most inventive workshops. Far from being barren wastelands, the frigid depths of space could be where nature perfects its recipes for life, one frozen molecule at a time. At temperatures so low they defy human comprehension, matter undergoes a transformation so strange it seems ripped from science fiction, the Bose-Einstein condensate. Imagine cooling a cloud of atoms to within a billionth of a degree above absolute zero, a realm where thermal motion nearly ceases. At this threshold, individual atoms lose their identities, merging into a single quantum wave that behaves as one colossal superatom. This isn't just laboratory curiosity, it's a window into how quantum weirdness might have influenced life's earliest chemistry. The eerie properties of these condensates reveal nature's hidden playbook. Under normal conditions, atoms bounce around independently, colliding and interacting in chaotic ways. But in a Bose-Einstein condensate, quantum coherence takes over. Particles move in perfect unison, like a school of fish turning as one. This synchronized dance allows effects normally confined to the microscopic world, like entanglement and superposition, to manifest on visible scales. Researchers have watched condensates split and recombine like liquid ghosts, demonstrating interference patterns that hint at quantum processes operating far beyond the atomic scale. What makes this relevant to life's origins? Consider the puzzle of how fragile biomolecules first assembled in the chaos of early Earth. Traditional chemistry assumes random collisions, but quantum effects like tunneling where particles bypass energy barriers could have provided shortcuts. In the deep cold of interstellar clouds or icy moon interiors, where Bose-Einstein-like conditions might arise naturally, molecules wouldn't need brute force collisions to react. Instead, they could feel out optimal configurations through quantum coherence, linking up with precision impossible in warmer environments. Lab experiments already show this potential. When scientists create condensates using rubidium or sodium atoms, they can simulate how quantum states might enhance molecular self-assembly. Some theorists propose that similar conditions in icy nebula pockets could have allowed prebiotic molecules to explore countless configurations simultaneously, collapsing into stable structures only when the right combinations emerged. It's as if the universe ran a billion chemical experiments in parallel with quantum physics as the lab technician. The implications stretch beyond chemistry. If Bose-Einstein condensates exist naturally in space, perhaps in ultra-cold molecular clouds or the magnetospheres of neutron stars, they could be cosmic quantum computers, silently optimizing reactions too complex for classical physics. Even on Earth, extremophiles in permafrost might exploit subtle quantum effects to survive, their enzymes leveraging tunneling to catalyze reactions in the deep freeze. This bizarre state of matter blurs the line between physics and biology. By studying how atoms behave when stripped of thermal noise, we're not just probing the quantum realm, we're uncovering a hidden toolkit the universe might have used to craft life's first delicate structures. The coldest places in existence could hold the warmest secrets, written not in heat, but in the quiet coherence of quantum whispers. Superconductivity defies our everyday experience. Materials that suddenly lose all electrical resistance when chilled to extreme temperatures, allowing current to flow forever without losing energy. This quantum phenomenon typically occurs near absolute zero, where atomic vibrations quiet down enough for electrons to pair up and glide effortlessly through a material's structure. But what if life in the universe's coldest pockets has found a way to harness similar principles? It's not as far-fetched as it sounds. Nature has a habit of repurposing physics in ways we're only beginning to understand. Take the humble bacterium Geobacter sulphurejucens. Found in oxygen-starved soils, it grows tiny protein filaments called nanowires that conduct electricity with startling efficiency, almost like biological superconductors. While not a true superconductor, this microbe's ability to shuttle electrons over long distances hints at how life might exploit quantum effects in frigid environments. Now imagine organisms adapted to the perpetual cold of Europa's subsurface ocean or the icy plains of Pluto. In those extreme conditions where thermal noise is minimal, evolutionary pressures could push biochemistry toward even more exotic solutions. The key lies in coherence, the same phenomenon that lets superconductors carry current without loss. In quantum biology, coherence allows particles to exist in multiple states at once, enabling ultra-fast energy transfer in photosynthesis or near-perfect navigation in migratory birds. At ultra-low temperatures, these effects could become even more pronounced. Enzymes might use electron tunneling where particles bypass energy barriers by jumping through them to catalyze reactions that would stall in warmth. Metabolic processes could slow to a crawl, yet achieve unprecedented precision by leveraging quantum shortcuts. Lab experiments already show tantalizing possibilities. When researchers cool photosynthetic proteins to cryogenic temperatures, they observe quantum coherence lasting far longer than at room temperature. This suggests that cold doesn't just preserve life's machinery, it might unlock quantum efficiencies warmth obscures. On icy moons or drifting comets, where molecules have millions of years to experiment, evolution could have stumbled upon superconductivity-like tricks to conserve energy or transmit signals across frozen cellular networks. The implications ripple beyond biology. If life can exploit superconducting principles, even indirectly, it redefines where we might find it. A methane-based organism on Titan wouldn't need watery veins to circulate nutrients, so it might rely on superconductive pathways in its icy structure instead. Or consider extremophiles in Antarctica's subglacial lakes. Their survival strategies could hint at how life bridges the gap between quantum physics and biochemistry. This isn't just speculation, it's a challenge to our assumptions. Superconductivity was once thought to exist only in metals chilled by liquid helium. Then came high-temperature superconductors defying expectations. Life, with its 4 billion years of R&D, might have discovered quantum tricks we've yet to replicate in labs. The universe's coldest places aren't just dead zones. They could be quantum playgrounds where life dances to a rhythm we're only starting to hear. The Fermi paradox presents a haunting contradiction. The universe should be teeming with life, yet we hear only silence. But what if we've been searching in all the wrong places? Our hunt for extraterrestrial intelligence has long fixated on Earth-like worlds, planets basking in the warmth of their stars. Yet the cosmos' coldest corners, frozen moons, rogue planets, and interstellar ice might be the perfect hideouts for life we barely understand. Imagine civilizations not built on sunlit surfaces, but thriving in perpetual darkness beneath miles of ice, their very existence undetectable to our telescopes. Take Europa's subsurface ocean, sealed under an icy crust thicker than Earth's deepest trenches. If life exists there, it wouldn't need sunlight, just geothermal vents and chemical gradients, a slow, steady rhythm utterly alien to our frenetic biosphere. Such ecosystems wouldn't produce the radio signals or megastructures we associate with technological civilizations. They might not even recognize the concept of space travel, their entire universe confined to liquid labyrinths under ice. The same could be true for Enceladus or the hypothetical oceans of exoplanets like K218b. These aren't civilizations waiting to be discovered. They're entire realms of biology operating on timescales and energies we're only beginning to fathom. Then there's the possibility of dormancy. On Earth, microbes like Deinococcus radiodurans survive cosmic radiation and extreme cold by essentially shutting down for millennia. Now picture a spacefaring species that mastered suspended animation, embedding themselves in icy comets or the frozen crusts of rogue planets. They could be drifting between stars right now, biological time capsules waiting for a gravitational nudge toward a habitable system. The universe is 13.8 billion years old, plenty of time for civilizations to rise, hibernate, and reawaken in cycles we can't yet perceive. Our assumptions about detection might also be flawed. SETI scans for radio waves, but a subsurface ocean civilization might communicate through bioluminescent pulses or chemical signals. Even their technology, if it exists, could be unrecognizable, built around cryogenic superconductors or geothermal energy harnessed from hydrothermal vents. The icy shells of their worlds would block most emissions we associate with advanced societies. They wouldn't be broadcasting into space, they'd be whispering through ice. The paradox dissolves when we consider that life in the cold might not want or need to be found. While we search for neighbors, they could be all around us, hidden in plain sight, thriving in conditions we once dismissed as barren. The great silence isn't evidence of absence. It's a clue that life's blueprint is far more adaptable and far more patient than we ever imagined. Interstellar travel forces us to confront a brutal truth. Even the nearest stars are impossibly far by human standards. At conventional speeds, reaching Proxima Centauri would take tens of thousands of years. But nature offers a provocative workaround: extreme cold. Across Earth's frozen landscapes, organisms from tardigrades to Arctic fungi demonstrate an astonishing ability to press pause on metabolism, surviving for centuries in suspended animation. These natural hibernators don't just endure the freeze, they reverse death's tide upon thawing, restarting biological processes as if waking from a nap. Scientists call it cryptobiosis, a state where life persists at less than 1% of normal metabolic activity. For spacefaring civilizations, this biological cheat code could rewrite the rules of interstellar travel. Cryonics companies already capitalize on this principle, preserving human bodies in liquid nitrogen at -196 degrees Celsius with hopes of future revival. While full human reanimation remains science fiction, breakthroughs in organ cryopreservation hint at its plausibility. In 2023, researchers successfully revived and transplanted rat kidneys stored at cryogenic temperatures, their cellular structures perfectly intact. The key lies in vitrification, replacing water with antifreeze compounds that prevent deadly ice crystals from forming. Apply this to entire organisms, and the implications become staggering. A crew frozen solid could theoretically cross the light years unharmed. Their biological clock stopped until arrival, but nature may have beaten us to it. Consider the Siberian permafrost, where scientists revived nematode worms frozen for 46,000 years. These microscopic explorers spent millennia in icy stasis before wriggling back to life as if no time had passed. Even more remarkably, some bacteria trapped in salt crystals for 250 million years have been coaxed back to activity. If simple earthly life can achieve such feats, why not complex organisms adapted to space's deep freeze? Evolution on icy exoplanets might have perfected suspended animation as a survival strategy, allowing life to spread between stars via frozen comets or drifting spores. The mechanics of interstellar hibernation could differ radically from our cryonics labs. Some theorize about organisms that replace their body fluids with natural antifreezes, like the glycerol-rich cells of Arctic fish. Others imagine creatures that dehydrate completely, entering a glass-like state until rehydrated by planetary thawing. The most exotic proposals involve quantum biological tricks, enzymes that leverage tunneling effects to repair cellular damage during waking cycles, or proteins that fold differently in extreme cold to preserve neural connections. This isn't just speculation, it's testable science. NASA Cryo-Egg project explores induced torpor for Mars missions, while the European Space Agency studies how artificial hibernation might protect astronauts from cosmic radiation. Each breakthrough peels back another layer of possibility, suggesting that the universe's vast distances aren't barriers but invitations to slow down, to wait, and to let the cold carry life further than warmth ever could. The next generation of telescopes won't just peer at distant worlds, they'll sniff them out, hunting for the faint chemical whispers of life in the atmospheres of frozen exoplanets. Imagine JWST's successor, equipped with sensors so precise they could detect a single molecule of methane floating above an ice-covered world light years away. These aren't pipe dreams. Missions like the Habitable Worlds Observatory, slated for the 2030s, are being designed to do exactly that: scan the thin atmospheric veils of planets where temperatures never rise above -100 degrees, searching for anomalies that scream biology. Take methane, a gas that on Earth is mostly produced by living organisms. On a warm planet, it could be written off as geological volcanoes or hydrothermal vents might be the source. But on a frozen world where most geological activity has long since ground to a halt, methane becomes far more intriguing. It shouldn't persist for long in such environments. Sunlight or chemical reactions would break it down. So if we spot it lingering in an exoplanet's icy atmosphere, especially alongside other gases like oxygen or nitrous oxide, the odds tilt toward something alive beneath the surface, exhaling in the dark. Oxygen is another telltale sign. On Earth, it's a byproduct of photosynthesis, but on an ice-locked planet with no surface vegetation, free oxygen would need another explanation. Subsurface oceans, kept liquid by geothermal heat or tidal forces, could host microbes that split water molecules for energy, releasing oxygen as waste. Over millennia, that gas might percolate upward through cracks in the ice, seeping into the atmosphere where telescopes could spot it. The combination of methane and oxygen would be particularly electrifying. On Earth, these gases react quickly and vanish unless life continuously replenishes them. Finding them together on a frozen exoplanet would be like catching smoke from a hidden fire. But biosignatures won't always be obvious. Some might hide in plain sight, disguised as ordinary atmospheric quirks. Take dimethyl sulfide, a compound only known to be produced by marine algae on Earth. Detecting it in the atmosphere of a world like Europa's larger cousins, icy exoplanets with subsurface seas, could hint at entire ecosystems thriving in sunless waters. Even the absence of certain chemicals might speak volumes. A lack of carbon monoxide, for instance, could signal something is consuming it, perhaps microbes similar to Earth's deep-sea vent organisms, which use the gas as an energy source. The real challenge lies in context. A single molecule might not confirm life, but a cocktail of anomalies, unusual gas ratios, seasonal fluctuations, or even isotopic signatures could build a compelling case. Future telescopes won't just collect snapshots, they'll monitor these worlds over years, tracking atmospheric changes that betray hidden activity. Imagine spotting a plume of water vapor erupting from an exoplanet's icy crust, laced with organic compounds, just as Cassini saw on Enceladus. Or detecting thermal hotspots where geothermal warmth melts the ice, creating transient lakes that release telltale gases. The hunt won't be limited to planets orbiting stars. Rogue planets adrift in interstellar space after being ejected from their solar systems might harbor subsurface oceans warmed by radioactive decay. With no star to illuminate them, these nomads would be invisible to traditional telescopes, but next-gen infrared instruments could pick up their faint heat signatures. If one showed traces of ammonia or hydrogen sulfide in trace amounts, it might hint at chemistry stirred by life's hand. This isn't science fiction. Every year, models grow sharper, instruments more sensitive. What seemed impossible a decade ago, detecting atmospheres on Earth-sized exoplanets, is now routine. The icy worlds we once dismissed as barren might be the very places where life's signature shouts loudest, preserved in the cosmic deep freeze. The universe's coldest corners aren't just hiding life's blueprint, they might be broadcasting it, waiting for us to tune in. Finding life beyond Earth, even in the form of a single microbe clinging to existence in Europa's dark ocean, would trigger one of humanity's greatest ethical dilemmas. We celebrate explorers like Columbus and Magellan, but their voyages brought devastation to indigenous cultures. If we probe the ice cracks of Enceladus or drill into Mars' frozen aquifers, could we become the invasive species this time? The moment we detect life, whether it's a phosphorescent plankton drifting in Pluto's subsurface seas or a silicon-based extremophile thriving in Titan's methane lakes, we must confront uncomfortable questions. Does intelligence grant us the right to study other life forms? Or does it come with the responsibility to protect them from our curiosity? Consider the Antarctic Treaty, which designates the continent as a scientific preserve free from military activity or resource exploitation. This fragile, ice-bound ecosystem, Earth's closest analog to extraterrestrial environment, is protected precisely because we recognize its uniqueness. Should Europa receive similar status before we even land there? Some astrobiologists argue for strict planetary protection protocols, treating icy moons as cosmic wilderness areas where robotic probes must undergo sterilization so rigorous it would make a hospital blush. Others counter that such caution could paralyze discovery. After all, how do we study life without interacting with it? The tension between preservation and exploration has no easy answers. The ethical web grows more tangled when we consider contamination. Every spacecraft we send carries stowaways earthly microbes tenacious enough to survive launch radiation and the vacuum of space. NASA Galileo probe was deliberately crashed into Jupiter to avoid accidentally contaminating Europa with terrestrial bacteria. But what if our probes discover life only to realize we've already introduced our own? The nightmare scenario isn't finding aliens, it's erasing them before we recognize them as such. This isn't hypothetical. When the Viking landers touched down on Mars in the 1970s, their heat sterilizers may have inadvertently baked away the very microbes they sought. Then there's the question of communication. If we encounter complex organisms, say, a multicellular creature swimming in the abyss of a Kuiper Belt object's underground ocean, do we have an obligation to make contact? Dolphins and octopuses demonstrate intelligence without technology, yet we keep them in aquariums. Would we treat alien sea creatures any differently? The SETI Institute's protocols for responding to intelligent signals focus on radio communication, but life in icy realms might communicate through chemical pulses or bioluminescent flashes we can't yet decipher. Misinterpretation could have consequences we can't foresee. Perhaps the most profound shift would be psychological. Humanity has spent centuries imagining we're the universe's sole conscious witnesses. Finding even microbial life elsewhere, especially if it shares no common ancestry with Earth life, would prove biology works differently than we thought. It could humble us, or it could ignite a new space race to exploit these organisms for medicine or industry. The icy moons orbiting Jupiter and Saturn may contain resources worth trillions, but they could also be the first examples of life independent from our own. Do we mine them or worship them? The choice would define our species for generations. This ethical maze has no map, but we're already sketching the boundaries. The Outer Space Treaty of 1967 prohibits nuclear weapons in orbit but says little about protecting alien ecosystems. New agreements are emerging. NASA's Office of Planetary Protection classifies missions based on contamination risk, and private companies like SpaceX now face scrutiny over their Mars ambitions. Yet these are earthly rules made by earthly minds. The life we find may force us to invent entirely new ethical frameworks, ones that consider rights not just for intelligent beings, but for entire alien biospheres. After all, in the eternal freeze of the cosmos, life, in any form, might be the rarest treasure of all. Climate change isn't just melting glaciers, it's cracking open Earth's frozen archives, releasing secrets that have been locked away for millennia. Across the Arctic, permafrost that's remained solid for tens of thousands of years is thawing at alarming rates, exposing everything from woolly mammoth carcasses to ancient plant matter. But the most startling discoveries aren't the remnants of extinct megafauna. They're the microbes waking up from a deep freeze that predates human civilization. In Siberia, scientists have revived bacteria frozen for 24,000 years, organisms that simply hit pause on metabolism until temperatures rose again. These Lazarus microbes aren't just surviving, they're reproducing as if no time had passed at all, challenging our understanding of life's limits. What makes these organisms so extraordinary is their resilience. Some, like the ancient Streptomyces bacteria recently revived from Canadian permafrost, produce antibiotic compounds unlike anything in modern medicine, a tantalizing hint that Earth's frozen frontiers could be pharmacies in disguise. Others carried genes for surviving extreme radiation or repairing DNA damage accumulated over centuries. These aren't just scientific curiosities. They're living textbooks on endurance, offering clues about how life might persist on icy worlds like Mars or Europa. But there's a darker side to this thaw. Alongside these beneficial microbes, researchers are uncovering pathogens frozen since the Pleistocene, viruses and bacteria that modern ecosystems have no defenses against. In 2016, a heat wave in Siberia activated anthrax spores from a decades-old reindeer carcass, triggering an outbreak that hospitalized dozens and killed a child. The parallels to space exploration are impossible to ignore. Just as we're drilling into permafrost to study ancient life, future missions might probe the ice shells of Europa or Enceladus, potentially disturbing ecosystems that have evolved in isolation for eons. Earth's thawing permafrost serves as a cautionary tale, a reminder that frozen environments aren't sterile lockboxes, but delicate biological vaults. When NASA designs missions to icy moons, they bake spacecraft at extreme temperatures to kill earthly microbes, recognizing the risk of contaminating alien ecosystems. Yet here on Earth, climate change is performing the opposite experiment, unintentionally exposing our biosphere to ancient organisms with unpredictable consequences. This unfolding drama holds urgent lessons for astrobiology. The microbes emerging from permafrost demonstrate that life doesn't just endure cold, it weaponizes it, using freezing temperatures as a preservation strategy. Some species form endospores with protective shells so tough they can survive the vacuum of space. Others produce cryoprotectant proteins that prevent ice crystals from shredding their cells, a trick that could inspire new ways to store vaccines or transplant organs. As we search for life on icy worlds, Earth's thawing frontiers remind us that the coldest places aren't biological dead zones, they're time capsules, preserving life's ingenuity across geological ages. The ethical implications ripple outward. If Earth's permafrost can harbor dormant pathogens for millennia, what might lie frozen in the Martian permafrost or the subsurface oceans of icy moons? Our planet's changing climate is conducting an uncontrolled experiment, one that could preview the risks of disturbing extraterrestrial ice without proper safeguards. Meanwhile, the very microbes that pose risks also offer hope. Their ability to survive deep time suggests life could persist in the universe's coldest corners, waiting out eons until conditions improve. In this paradox lies a profound truth. The same ice that preserves life's past might hold the key to its future, both on Earth and among the stars. Artificial life experiments are rewriting the rules of biology by starting from the ground up, literally. In labs across the world, researchers mix simple chemicals like formaldehyde and hydrogen cyanide in ultra-cold chambers designed to mimic the void of space. Then watch as these ingredients spontaneously arrange into more complex structures. One groundbreaking study at the University of Chicago saw amino acids emerge from a simulated interstellar ice bath chilled to -260 degrees Celsius, proving that the building blocks of life can self-assemble without Earth's warmth or liquid water. These reactions unfold at a glacial pace, sometimes taking weeks to produce a handful of molecules. Yet that sluggishness is precisely what allows delicate structures to form without falling apart. The goal isn't just to recreate life's ingredients, but to engineer entirely new biological systems from scratch. At the J. Craig Venter Institute, scientists have built synthetic cells with minimal genomes, stripped down DNA blueprints containing only the genes essential for survival. When incubated in near-freezing conditions, these artificial organisms exhibit eerie resilience, slowing their metabolism to a crawl to withstand environments that would kill natural cells. Some teams are pushing further, crafting protocells with membranes made of fatty acids that could have formed in icy comet cores, or designing RNA molecules that replicate themselves without enzymes, a potential precursor to life's first genetic code. What makes these experiments so revolutionary is their dual insight. They not only suggest life could arise spontaneously in the universe's frigid corners, but also reveal how adaptable its core machinery might be. In one tantalizing trial, researchers at Harvard modified a synthetic bacterium to survive on methanol at temperatures mimicking Europa's subsurface ocean. The microbe didn't just endure the cold, it thrived, evolving novel proteins that functioned better in the freeze than at room temperature. This hints that life, given the right conditions, might not just emerge in the cold, but optimize itself for it. Yet the most profound question remains unanswered. Is life's emergence a cosmic inevitability or a statistical fluke? Cold lab experiments tilt the scales toward inevitability. When Pittsburgh scientists recreated the icy plumes of Enceladus in a vacuum chamber, blasting water, ammonia, and methanol with radiation, they found nucleobases, the letters of DNA, forming within days. Similar studies in Japan produced peptide bonds, the links between amino acids, in frozen mixtures exposed to ultraviolet light. The universe, it seems, has a knack for stumbling toward complexity wherever temperatures drop low enough to preserve fragile chemistry. Critics argue these experiments still lack the spark of true life. No synthetic cell has yet achieved consciousness, evolution, or autonomous reproduction. But that might miss the point. These lab creations aren't meant to mimic modern biology. They're windows into life's humblest beginnings. Like a chef reducing a sauce to its essential flavors, scientists are distilling biology to its simplest possible form, revealing how little it might take to cross the threshold from chemistry to life. Every time a synthetic cell divides in a frost-coated Petri dish, or a strand of lab-made RNA copies itself in a freezer, we're glimpsing the universe's quiet persistence, its relentless drive to turn stardust into something that, against all odds, can call itself alive. The Europa Clipper spacecraft, set to launch in 2024, isn't just another robotic explorer, it's a cosmic detective armed with instruments fine-tuned to sniff out life's faintest whispers. Unlike earlier missions that snapped photos from afar, Clipper will dive deep into Jupiter's radiation belts, performing 45 close flybys of Europa's fractured, icy surface. Its ice-penetrating radar will map the thickness of the Moon's frozen shell, searching for hidden pockets of liquid water suspended like bubbles in an ice cube. Meanwhile, a thermal imager will scan for heat signatures betraying recent eruptions, while a mass spectrometer analyzes any geyser plumes for organic molecules. But the real game changer, its ultraviolet spectrograph, capable of detecting amino acids or fatty acids compounds that don't form easily without biological processes. If Europa's ocean harbors even microbial life, Clipper could catch its chemical fingerprints on the ice grains ejected into space. Dragonfly NAS, a rotorcraft destined for Titan's methane-soaked dunes, takes exploration to another level. This nuclear-powered drone will hop across Saturn's largest moon like a robotic dragonfly, sampling surface chemistry in locations hundreds of miles apart. Titan's thick atmosphere and low gravity make flight surprisingly efficient, allowing Dragonfly to scout icy volcanoes, hydrocarbon lakes, and even potential cryovolcanic flows, places where water might briefly mix with organic rich sludge. Its drill will bore into the surface, testing for molecules like vinyl cyanide, which could form cell-like membranes in liquid methane. What makes Dragonfly revolutionary isn't just its mobility, it's the mission's willingness to embrace Titan's alien chemistry. While Europa Clipper looks for life as we know it, Dragonfly asks a bolder question. What if life here operates by rules we've never imagined? These missions represent a seismic shift in astrobiology. For decades, the search for life focused on Mars, a planet that, while fascinating, may have lost its habitable potential billions of years ago. Europa and Titan, by contrast, offer environments where life could persist today, shielded from cosmic radiation by miles of ice and energized by tidal friction or chemical reactions. Clipper and Dragonfly are just the vanguard. The European Space Agency's JUICE mission will study Ganymede's subsurface ocean, while concepts like Enceladus Orbilander propose landing directly on the geyser-spewing moon to sample its plumes. Each probe carries instruments orders of magnitude more sensitive than their predecessors, capable of detecting molecular patterns that would have been invisible even 10 years ago. Yet the most profound discoveries might come from unexpected places. Consider Trident, a proposed mission to Neptune's bizarre moon Triton. This icy world, likely a captured Kuiper belt object, boasts nitrogen geysers and a subsurface ocean that could be rich in ammonia, a potent antifreeze. Or the planned Habitable Worlds Observatory, a space telescope designed to scan exoplanet atmospheres for biosignatures, which might spot methane or oxygen on frozen worlds orbiting red dwarfs. The universe's coldest habitats are no longer theoretical. They're targets on a star map waiting to yield their secrets. What makes this new era so electrifying isn't just the technology, it's the philosophy. We've moved beyond simply hunting for water. Now we're probing how life might hack chemistry in extreme cold, whether through quantum tunneling in enzyme reactions or novel solvents like methane. A single unambiguous detection, a cell, a fossil, or even an imbalance in gas ratios that defies geological explanation would prove life isn't a fluke confined to Earth. It's a cosmic imperative, thriving wherever conditions allow, even in the darkest, coldest corners of existence. The ice isn't a barrier, it's a veil, and we're finally ready to lift it. From the Boomerang Nebula to the hidden oceans of Europa, the universe's coldest places aren't just barren wastelands, they're cosmic kitchens quietly simmering with the ingredients of life. Think about how absurd this would have sounded a century ago, the idea that temperatures near absolute zero, cold enough to freeze atoms in their tracks, could be anything but lethal to biology. Yet here we are, uncovering frozen amino acids in interstellar clouds, reviving microbes after millennia in permafrost, and spotting complex organics in the plumes of icy moons. These discoveries don't just expand the boundaries of where life might exist, they rewrite the recipe entirely. Take the humble tardigrade, a microscopic creature that shrugs off the vacuum of space by dehydrating its body into glass-like stasis. Or the Antarctic bacteria that thrive in subglacial lakes, cut off from sunlight for millions of years, surviving on chemical energy from rocks. These extremophiles aren't flukes, they're proof of life's relentless ingenuity. Now stretch that ingenuity across the cosmos. On Europa, where tidal forces churn a saltwater ocean beneath miles of ice, or Titan, with its methane rivers and hydrocarbon dunes, evolution could have crafted organisms so alien they defy our textbooks. Life here wouldn't just endure the cold, it would weaponize it, turning freezing temperatures into an advantage. The implications ripple far beyond our solar system. Every frozen exoplanet orbiting a dim red dwarf, every rogue planet drifting between stars, becomes a potential habitat. Imagine a world where photosynthesis is impossible, but geothermal vents fuel ecosystems in perpetual darkness. Or a methane-based life form that reproduces once every 1,000 years, its metabolism slowed to match the glacial pace of its environment. These aren't sci-fi fantasies, they're testable hypotheses, guided by the bizarre life forms we've already found in Earth's most inhospitable corners. What makes these frozen realms so compelling isn't just their potential to host life, it's how they preserve it. Ice acts as nature's time capsule, safeguarding delicate molecules for eons. The Murchison meteorites' ancient amino acids, the organic-rich plumes of Enceladus, even the hypothetical microbes hibernating in Martian permafrost all owe their survival to the deep freeze. In a universe where heat accelerates decay, cold becomes life's silent ally, pressing pause on destruction long enough for complexity to emerge. As probes like Europa Clipper and Dragonfly prepare to explore these icy frontiers, we're on the brink of something extraordinary. A single discovery, a cell, a fossil, or even an unexplained chemical imbalance could prove that life isn't a rare accident, but a cosmic inevitability. The universe's coldest places aren't the end of the story. They might be where it begins. If these cosmic mysteries have left you as awestruck as they've left scientists, don't let the conversation end here. Smash that like button and subscribe to join us on more mind-bending journeys through the universe's greatest puzzles. Every click fuels our mission to explore deeper, stranger corners of space, from the icy plumes of Enceladus to the quantum quirks of distant nebulae. But we want to hear from you too. Where do you think life will show up next? Could it be swimming in Europa's hidden ocean, drifting through Titan's methane rivers, or maybe even clinging to some rogue planet in the void between stars? Drop your boldest theories in the comments, whether you're Team Microbe or Team Alien Civilization. This is your chance to weigh in. And if you've got a space mystery you're dying to see us tackle next, shout it out. Together, we're not just passive viewers, we're active explorers, piecing together the universe's grandest secrets one discovery at a time. So hit subscribe, turn on notifications, and let's keep unraveling the cosmos, because the next breakthrough could be just one video away.